Let's dive right in with our opening puzzle. Imagine a barn that holds 50 animals. Some of them are chickens and some of them are horses. Of course, chickens have 2 legs and horses have 4. Now, suppose I tell you there are a total of 140 legs. How many chickens and how many horses are there? I have fond memories of this problem. My older brother had it as a homework problem in an algebra class, and I remember being in the room as he discussed it with my father, who likes mathematical puzzles. Indeed, this sure sounds like a standard algebra problem. In fact, if you find that I'm bringing back bad memories of high school algebra, then I urge you to bear with me a little longer. There's a punchline at the end of this puzzle. Now, how would we approach this as an algebra problem? Well, we'd probably begin by defining some variables to represent the number of chickens and the number of horses. Let's use C to represent the number of chickens and H to represent the number of horses. Well, since there are 50 animals in all, we can write the equation C plus H equals 50. Well, each chicken contributes 2 legs, and each horse contributes 4 legs, and that gives us the equation 2 times C plus 4 times H is 140, since there are 140 legs in total. In other words, the number of chicken legs is twice the number of chickens, and the number of horse legs is 4 times the number of horses. We can now use standard algebra techniques to solve these 2 equations. The first equation tells us that C is equal to 50 minus H. We can substitute that into the second equation to get 2 times 50 minus H plus 4H equals 140. And this equation simplifies to 100 minus 2H plus 4H, which of course is 100 plus 2H, and that's going to equal 140. And finally, this implies that 2H equals 40, and therefore that there are 20 horses. And if there are 20 horses, then there must also be 30 chickens. Problem solved. Phew. Now, keep in mind, I'm a professional mathematician. I love algebra, and manipulating equations like that gives me a warm, fuzzy feeling that lasts for hours. It's been suggested to me, however, that not everyone loves algebra quite as much as I do. And if you're one of those people, then I promise this is the right lesson for you. Because now we come to the punchline that I promised. You see, if solving a system of equations were the final word on this puzzle, I would not have included it in this course. But it's not the end of the story. My brother's teacher showed the class a delightful method for solving this puzzle that uses no algebra at all. The trick is to tell all the horses to stand on their hind legs. Now, all of the animals have 2 legs on the ground. And since there are 50 animals, that means there are 100 legs on the ground. And since there were 140 legs total, that means there are 40 legs in the air. Each horse has 2 legs in the air, implying there are 20 horses. And that means there are also 30 chickens, and we've arrived at precisely the same answer as before, only with way less algebra. People often think that mathematics and mathematical reasoning are all about manipulating symbols according to incomprehensible rules. Not at all. Real mathematics, not the annoying grade school caricature, is about solving problems, and that's all. The symbols and the algebra and the rules are just useful tools in our arsenal, but we don't wield them for their own sake. Rather, we do what's necessary to solve the problem, whatever the problem happens to be. And that's our theme in this lesson. As with our opener, all of the puzzles in this lesson seem to have a straightforward algebraic solution, but they can also be solved with just a bit of cleverness and clear thinking. As the title says, you don't need no algebra. Actually, that title comes from a chapter in a book of puzzles by Raymond Smullyan. We'll be seeing a lot of his work when we start discussing logic puzzles in the next lesson. But in his book, Alice in Puzzleland, he has a character present a series of puzzles that are right up our alley. After presenting each puzzle, the character says, you don't need no algebra. In presenting today's puzzles, I'll sometimes invite you to pause the video and work them out yourself. We'll discuss the mundane mathematical solutions along with the puzzles themselves, but we'll also reveal the clever non-algebraic solutions. Here we go. Our first puzzle is this. Suppose we have a collection of treats we're going to give to some dogs and cats. We'll assume there are a total of 30 animals and 100 treats. Each cat gets 3 treats, but the dogs, since they're bigger and hungrier, get 4 treats each. How many dogs and how many cats do we have? Okay, let's walk through the algebraic approach together. If C is the number of cats and D is the number of dogs, then we have C plus D equals 30. Since each cat gets 3 treats and each dog gets 4 treats, we get the equation 3C plus 4D equals 100. And working through the problem, just as we did with the horses and chickens, we know that 3 times 30 minus D plus 4D equals 100. This eventually simplifies to 90 plus D equals 100. And this tells us that D equals 10. So there are 10 dogs and 20 cats. But you know what's coming next, right? You don't need no algebra. A bit of clear thinking and calm reflection should be sufficient. Of course, you could do this by trial and error. That is, you could just pick random guesses for the number of cats and the number of dogs, and I suspect it will not take you long to converge on the correct answer. I deliberately chose very small numbers so that the solution will be easier to follow. I think we can agree, though, that trial and error is not really in the spirit of things. I could have chosen very large, awkward numbers that would make trial and error impractical, but the really slick approach I'll show you will still work just as well. Can you figure it out? Put me on pause to give it a try. So, we have a group of 30 dogs and cats and 100 treats to divide among them. Cats get 3 treats and dogs get 4 treats. We need to work out how many dogs and how many cats there are without writing down any equations. Here's what you could do. Start by giving all the animals 3 treats. Since there are 30 animals, that accounts for 90 treats. But each dog has 1 more treat coming to him. And since there are exactly 10 treats remaining, that means there are 10 dogs and 20 cats. The same answer we got before. Very clever, and no algebra required. Let's try another one, also based on a puzzle from Raymond Smullyan. 2 people, let's call them Alice and Bob, were enjoying some cookies. Alice had 3 times as many cookies as Bob. Finding this unfair, Bob asked Alice to give him some of her cookies. Alice handed over 1 of them. Bob said, "This still isn't fair. Now you have twice as many cookies as me." The question is, how many more cookies must Alice give to Bob so that they have the same number? And no, I didn't forget to tell you how many cookies there are in total. You just don't need that piece of information. Once again, this readily yields to a bit of algebra. Just let A represent the number of cookies Alice has, let B represent the number of cookies Bob has, and with a bit of patience, you can quickly summon forth equations that will help you solve the puzzle. But one more time, you don't need no algebra. Can you solve it? Take a minute to think it through. Okay, we said that Alice starts with 3 times as many cookies as Bob. After Alice gives Bob 1 cookie, she only has twice as many cookies as Bob. Well, the first observation is that saying that Alice has 3 times as many cookies as Bob can be interpreted to mean that 3 out of every 4 cookies are Alice's and 1 out of every 4 is Bob's. In other words, Alice has 3/4 of the cookies and Bob has 1/4. Likewise, after Alice hands over 1 of her cookies, thereby producing a situation in which she has only twice as many cookies as Bob, we can say that Alice now has 2/3 of the cookies compared to Bob's 1/3. Reasoning as before, if Alice has twice as many cookies as Bob, then 2 out of every 3 cookies are hers and 1 out of every 3 is Bob's. That means that 1 cookie represents the difference between 3/4 of the cookies and 2/3 of the cookies. But 3/4 minus 2/3 works out to be 1/12. In other words, 1 cookie represents 1/12 of all the cookies, which means that there are 12 cookies in all. Let's see if this works. Initially, Alice must have had 9 cookies to Bob's 3, since she had 3 times as many cookies and there are 12 in all. After handing over 1 cookie, Bob had 4 and Alice had 8, which is twice as many. And since the question asked for the number of cookies Alice must give to Bob for them to have the same number, the answer is that she must give him 2 more, after which they will both have 6. A very elegant solution, I think. Here's one more from Smulyan before we move on. The king of the realm hired a gardener to do some work for him. The gardener was hired for 26 days. To sweeten the deal, literally, the king decreed that for each day the gardener worked, he would receive 3 tarts. But in return, the gardener would have to pay the king a tart for each day he was idle. At the end of the 26 days, the gardener had 62 tarts. How many days did he work? A straightforward algebra problem once again. Let x be the number of days the gardener worked. Then 26 minus x represents the number of days he was idle. So his total haul of tarts is 3x minus 26 minus x, which must equal 62, and we can go from there. But where's the fun in that? Say it with me now, you don't need no algebra. Time to put me on pause to see if you can come up with a different way to solve this puzzle. Okay, the deal was that the gardener would be employed for a total of 26 days. For each day that he worked, he would receive 3 tarts, and for each day he was idle, he would owe the king 1 tart. At the end of his employment, we are told he had 62 tarts. How many days did he work? The key is to notice that if the gardener had worked every day, then he would have 26 times 3 tarts, which makes 78. In reality, he only finished with 62. The only way to lose tarts from the 78 is to remain idle. For each day he's idle, he effectively loses 4 tarts. Do you see why? Well, he has to pay the king 1 tart for his idleness, but he also loses the 3 tarts he would have gotten from working. Now, he lost 16 tarts total, and since he effectively loses 4 tarts for each day he's idle, he must have been idle on 4 days. And that gives us the answer to the question. He worked a total of 22 days. Now let's move on to a few famous puzzles. Perhaps you've seen single elimination competitions like March Madness in college basketball, or maybe a big tennis tournament. They start with 64 competitors, players in tennis or teams in basketball, and play a series of matches until there's one winner at the end. Single elimination means that after losing 1 match, you're out. The question is, when the tournament is complete, how many matches will have been played? In this case, the obvious solution is not so much algebraic as it is arithmetic. We can just figure out how many matches are played in each round and then add them all up to get the answer. Let's say we're dealing with a 64-player tennis tournament. In the first round, the 64 players will compete in 32 matches, leaving 32 competitors standing at the end of the first round. In the second round, those 32 competitors will compete in 16 new matches, after which 16 competitors will remain. The number of matches is cut in half in each round. There will be 8 matches in the third round, then 4, then 2, and then 1 match in the finals. So the total number is 32 plus 16 plus 8 plus 4 plus 2 plus 1, and that's 63. Very nice. How about we make the puzzle a little more interesting? This time you have some number, let's call it n, of players. I'm not going to tell you what n is. It might not even be a power of 2, which means there might be some rounds in which only an odd number of players remain. These n players play a single elimination tournament. We stipulate that if there's ever an odd number of teams remaining, well, then there's some system of buys in place to determine who doesn't play in that round. When we reach the end of the tournament, there's only 1 player left standing. At that point, how many matches will have been played? I promise that you have enough information to solve the problem. Put the video on pause and see what you can come up with. Okay, We worked out explicitly that when we start with 64 players, the answer turns out to be 63 matches played, one less than the number we started with. It turns out that this is a general pattern. The answer to our question is that if we start with n players, the tournament must involve precisely n-1 matches. Let's see why this is so. The trick is that rather than count matches, you need to count losers instead. Every match has one winner and one loser. But at the end of the tournament, there's one winner and n-1 losers. To produce n-1 losers, you must have n-1 matches. So, if you have 7 players, you need 6 matches. 113 players, 112 matches. Simple as that. The answer is n-1, and you don't need no algebra. Let's close this lesson with 2 true classics of the genre. Imagine that there's a horse who normally gallops at a speed of 10 miles per hour. One day, the horse gallops some distance, we don't know how far specifically, and then immediately turns around and gallops right back to where he started, retracing the same path. The next day, the horse undertakes the same trip, but this time he gallops on a treadmill that is moving at 2 miles per hour. So during the first part of the trip, the horse is galloping with the treadmill and is therefore moving faster than he would on his own. But on the return trip, he's galloping against the treadmill and is therefore moving more slowly than he would on his own. The question is, which trip took longer? The round trip on the first day or the round trip on the second day? Well, the algebraic approach would be to let, say, d represent the one-way distance and to then work out explicitly how long each trip took in terms of d. It's a very practical, reasonable approach to the problem. But if you think that's the end of the story, then perhaps you've missed the point of the lesson. Let's work through this one together. To keep things simple, we'll assume the whole trip was a mere 1 mile. Since the horse travels at 10 miles per hour, he'll need 6 minutes to go 1 mile. Therefore, a round trip of 2 miles will require twice that, which is 12 minutes. That's the first trip. How does the treadmill affect things? Well, you might assume that the 2 trips take the same amount of time, since the extra 2 miles an hour on the first leg of the trip are exactly canceled out by the reduction of 2 miles an hour on the return trip. But is that correct? Well, since the treadmill accelerates the horse by 2 miles per hour, the first mile of the trip will be carried out at 12 miles per hour. At that speed, a 1 mile trip requires 5 minutes. On the return trip, the treadmill slows the horse down to 8 miles per hour. And now a 1 mile trip requires 7.5 minutes. The whole trip therefore takes 12.5 minutes, which is longer than the trip without the treadmill. So it seems that the argument that working with the treadmill for half the trip and then working against the treadmill for half the trip perfectly cancel out is not correct. But what went wrong? I'd suggest that the confusion arises from the phrase half the trip. If we take this to mean half the time, then the argument would be correct. Let's do an example to illustrate this. Suppose we travel at 12 miles per hour for 1 hour and then at 8 miles per hour for 1 hour. That means that we go 12 miles the first hour and 8 miles the second hour for a total of 20 miles. But if we had traveled at 10 miles per hour for 2 hours, we would have gone the same 20 miles. But that's not the scenario of this puzzle. In our context, half the trip means half the distance. That's entirely different. Specifically, the difference is that the first mile, undertaken at 12 miles per hour, is traveled more quickly than the second mile, undertaken at 8 miles per hour. In other words, the time during which the treadmill slows you down is longer than the time during which the treadmill speeds you up. And that's why the whole trip takes longer with the treadmill than it does on normal ground. And this conclusion holds regardless of the total distance of the trip. Problem solved, and with no algebra required. Incidentally, the logic of this puzzle has a practical application. Suppose a plane flies from New York to San Francisco. The next day, the plane makes the return trip from San Francisco to New York. Even if we assume the plane took exactly the same flight path and that the weather and wind conditions were precisely identical, it will still be true that the return trip takes longer. Why? Well, because the Earth rotates west to east. That means that when you take off from New York, while you're in the air, the Earth helpfully rotates slightly in your direction, bringing San Francisco just a little closer. On the return trip, the rotation of the Earth works against you. Don't say I never taught you anything useful. And that brings us to our final puzzle for today's lesson. It's a true masterpiece, so it's definitely one you want to carry around with you. It goes like this. We have a glass with 5 cups of water and another glass with 5 cups of wine. We remove 1 cup of water from the water glass and drop it into the wine glass. Then we stir the water-wine mixture until it's thoroughly stirred so that the water is evenly distributed in the wine. We now remove 1 cup of the mixture and place it back into the water glass, again stirring thoroughly. The question is this: when we're done, is there more water in the wine glass or wine in the water glass? As usual, pause the video here to think that over. The most natural way to solve this problem would be to work out precisely how much water is in the wine glass and also how much wine is in the water glass. So let's see. First, we removed 1 cup of water from the water glass and placed it in the wine glass. At this moment, there are 6 cups of liquid in the wine glass. We then stir this mixture. The cup of the mixture will then consist of 5/6 of a cup of wine and 1/6 of a cup of water. So the final tally is that there is 5/6 of a cup of wine in the water glass after the 2 transfers. On the other hand, we initially put 1 cup of water into the wine glass, but then removed 1/6 of a cup. That means there is 5/6 of a cup of water in the wine glass. In other words, the amount of water in the wine glass is the same as the amount of wine in the water glass. Now, that's a perfectly acceptable solution, but it's really not in keeping with the theme of today's lesson. So let's see how we might have arrived at this answer without having to calculate anything. The key observation is that each glass has the same amount of liquid at the end as it had at the beginning. So the amount of water that left the water glass must have been replaced by exactly that much wine. And where did the missing water go? It all went into the wine glass. In fact, we could have made the puzzle harder. Let's say that this time we have a glass of water and a glass of wine, but we don't know how much of each that we have. We transfer some water into the wine glass and stir, but this time we make no particular effort to stir thoroughly so that we don't know that the water is distributed evenly in the wine. Then we transfer some of the mixture back to the water glass and stir. We keep transferring liquid back and forth some number of times, but we don't know how many. The only thing we do know is that each glass has the same amount of liquid at the end of the process as it did at the start. I now ask the same question. Is there more water in the wine glass or wine in the water glass? Incredibly, we still have enough information to solve the puzzle. All that matters is that each glass ends with exactly as much liquid as it began. That means that any water that left the water glass was replaced by exactly that quantity of wine. And since all of that water that we removed was placed in the wine glass, we see once more that the amount of water in the wine glass is the same as the amount of wine in the water glass. This is a fine illustration of the principle that sometimes having too much information can actually make a problem harder to solve. Sometimes knowing too much can distract you from what's really important. And that'll do it for today. See you next time.